So the most common way that we're going to end up dealing with conservation of momentum is during a collision. And so a collision is defined to be a brief, intense interaction between objects. And so those first two words are pretty important. So the brief tells us that it happens during a short time of the object's motion, which means that collisions happen quickly. And because they happen quickly, the objects involved in them don't have the time to move around. So potential energies can largely be neglected in terms of thinking about how the energy is changing during a collision. Which means that in terms of thinking about the energy during a collision, we're largely going to think about what's going on with the kinetic energy. The intense part tells us that the forces between our interacting objects are much larger than any external forces that are acting on the objects. This means that collisions are dominated by internal forces rather than external forces. So the effect here is that the external forces acting on our system, they're basically negligible. So if we have any, and we can certainly envision collisions where we don't have any at all, but if we do have external forces, by and large, we're going to be able to ignore them because their effect will be much, much less than these internal forces as these pieces interact with each other during the collision. What this means then is that during a collision, our system is effectively an isolated system. And we know that momentum is always conserved for an isolated system. So we won't have our net impulse exerted on the system is going to be zero, which means that momentum will be conserved. So we'll be able to set up an equation that tells us that the initial momentum of our system is going to be equal to the final momentum of our system. So that's what's going on with momentum during collisions. It's always going to be conserved. At least it's always going to be conserved for the system. So if we consider all the pieces that are involved in the collision, then we can talk about conservation of momentum. But of course, we've talked about a second conservation law this semester, the conservation of energy. And what's going on with energy is dictated by the type of collision you have. So notice that there are four basic types of collisions. There's totally inelastic, partially inelastic, elastic, and superelastic. And so these first two, these inelastic collisions, these are situations where energy is lost. So when we think about the energy during a collision, again, part of the argument we were making about what the brief tells us is that during the collision our objects won't have time to move so that the potential energy will be changed. So what we're going to keep track of is the kinetic energy. And when you calculate the change in the kinetic energy, so literally just the kinetic energy of the system at the end, final, minus the kinetic energy of the system at the beginning, delta K is negative for inelastic collisions. You have lost some of the kinetic energy of the system. Now, if you have a totally inelastic collision, you know that it's totally inelastic because your pieces stick together. So basically a totally inelastic collision, you've lost as much energy as you possibly can because that energy has gone into making those pieces stick together. A partially inelastic collision, on the other hand, you're still going to lose some of that kinetic energy, but your objects don't stick together. They bounce off each other, but they don't bounce off each other elastically, so energy will be lost. So for both of these inelastic collisions, momentum is still conserved because momentum's always conserved with our collisions, but energy is not. Energy is lost. On the other hand, if my two pieces collide and bounce off each other elastically, well, that elastic part means that effectively when they're in contact, they're converting the kinetic energy into elastic potential energy and then recovering all that energy back as they bounce off each other. Which means that the elastic collision is the one special case where energy is conserved. And so just to make it as clear as possible, elastic starts with E, energy starts with E. So this is just the easiest way to try and remember what special case of collisions energy will be conserved. So how do you know you have an elastic collision? Well, either you have to be told that your collision is elastic, or You go through and work the conservation of momentum problem. And once momentum is conserved, you calculate delta K, and if the change in kinetic energy is 0, then you know you have an elastic collision. So this is the one case, the elastic collision is the one case where both momentum and energy are conserved. But if you're not told that up front, that energy conservation is not particularly very useful. Again, you may just have to start with momentum conservation and then go calculate out and see that what you have is an elastic collision. Our fourth type is a superelastic collision. In a superelastic collision, we've talked about energy being conserved during an elastic collision and lost during an inelastic collision. Well, a superelastic collision is our other option where we actually have gained energy. So you have more kinetic energy at the end than you had at the beginning. So delta K is positive during a superelastic collision. And there are a couple ways that we can sort of have a superelastic collision. One is you can have some sort of potential energy that you're basically releasing during the collision. So one way to do this is, let's say you have two blocks colliding, but one of those blocks has a spring, and that spring happens to be loaded, but then that spring releases when the blocks collide. So in that case, what you have is you have more energy at the end because you've also converted that elastic potential energy that the spring was storing. You've converted that into kinetic energy as well. The second way to sort of have a superelastic collision is really something that we don't often think of as collisions, but it's basically an explosion. So instead of having two objects and slamming them together so that they stick together, an explosion says I'm going to start with a single object and I'm going to blow it apart. So you can think of an explosion as a collision that's being run in reverse. And so what happens is that you have, usually with an explosion, it's a chemical potential energy that again is being converted into kinetic energy to make your pieces move faster at the end than what they were at the beginning. So we can sort of, either of these ways are ways to end up gaining kinetic energy during the collision. And so we'll want to think about, obviously, if we have a spring, that's going to be an easy indicator. But then also if we have an explosion, so our collision's running in reverse, that's going to be the other way to sort of identify or expect to have a superelastic collision where we know that we're going to end up gaining energy.